Welcome to Schrödinger's Chat, the podcast where I explore the real science behind the biggest questions in the universe, as well as some of the quirkier science we encounter every day. I'm Anna, a sixth form physics student with a lot of curiosity and a passion for understanding how the world works. From the smallest particles to the largest galaxies, join me as we unlock the mysteries and wonders of the universe and explore how physics shapes the world around us. Physics can be beautiful and elegant, but it can also be absolutely wild. So today, I'm taking you to some of the most extreme corners of the universe. The hottest temperatures, the coldest places, and the most crushing pressures. We're exploring what happens when physics is pushed to its absolute limits. Imagine places colder than interstellar space, pressures that can squash atoms into exotic forms, and speeds so fast they stretch time itself. This is a world of extreme physics, and it's stranger and more wonderful than science fiction. So get comfy and maybe grab a blanket, because we're starting with the coldest places in the cosmos. Now, when you think of extreme cold, things like winter, ice, and Antarctica spring to mind. Antarctica does hold the record for the coldest temperature ever recorded on Earth, which is negative 89.2 degrees Celsius, recorded at Russia's Vostok research station on the 21st of July 1983. However, even this is nowhere near the extreme end of cold temperatures. You've probably heard of absolute zero. It's the coldest temperature theoretically possible. That's 0 Kelvin, which is negative 273.15 degrees Celsius. At absolute zero, atoms stop moving. Well, almost stop. At those temperatures, matter behaves in really strange ways, and you get things like Bose-Einstein condensates, where atoms start acting as one superatom. This is where these extremely cold atoms and subatomic particles come together to form a single superatom that can be described by a wave function. And quantum effects that are only usually visible on very small scales can be observed on a macroscopic scale. Albert Einstein predicted this type of matter in 1942, using the ideas of the Indian physicist Satyendra Nath Bose. This is where the name Bose-Einstein condensate comes from. We've actually come extremely close to reaching absolute zero on Earth. In 1995, scientists managed to cool a gas of rubidium atoms to just a few billionths of a Kelvin above absolute zero. More recently, in 2015, scientists at MIT managed to cool sodium-potassium gas to just 500 nanokelvin. That's just half a billionth of a degree above absolute zero. And believe it or not, we've got even closer than that. In 2021, the record was broken by a team of German physicists who managed to cool rubidium gas to 38 picokelvin, or 38 trillionths of a degree above absolute zero. Now that's just incomprehensibly cold. Bose-Einstein condensates aren't just about seeing how close to absolute zero you can get, they have real applications. They can be used to create advanced, high-precision measurement technology and sensors. For example, they have potential to be used to detect gravitational forces or improve navigation systems and medical imaging technology. Bose-Einstein condensates also help scientists to model and study complicated quantum phenomena and systems. It allows them to kind of see quantum phenomena happen in slow motion. So the coldest place in the known universe right now isn't in deep space. It's a lab in Germany where scientists cooled atoms to within 38 trillionths of a Kelvin. Now let's crank the dial the other way and talk about extreme heat. The hottest temperature recorded on Earth is 56.7 degrees Celsius, measured on the 10th of July in 1913 at Furnace Creek Ranch, very appropriately named, in Death Valley, California. Way hotter than this, the sun's core is about 15 million degrees Celsius. That's pretty warm, but that's nothing compared to what we can create in particle accelerators. At CERN's Large Hadron Collider, scientists have smashed particles together with such energy that they've briefly recreated the conditions just moments after the Big Bang, hitting temperatures of trillions of degrees Celsius. Right after the Big Bang, the universe was about 10 to the power of 32 Kelvin. In 2012, at CERN, temperatures of 5.5 trillion Kelvin were created when lead atoms collided. That's way hotter than even the core of a star. At those trillion-degree temperatures, matter doesn't even behave normally. Protons and neutrons melt into a soup of quarks and gluons, which is called quark-gluon plasma. So scientists are basically recreating the conditions of the early universe in Switzerland. No big deal. Next, let's talk about pressure. Here on Earth, we're used to atmospheric pressure, about 1 atmosphere at sea level. The Mariana Trench, which is the deepest part in the ocean, has a pressure of about 1,100 times atmospheric pressure. But deep inside Earth, it's a whole different story. At the Earth's core, pressures reach about 3.6 million atmospheres. For some perspective, that's like having 1,000 Eiffel Towers balanced on your head. Pretty crushing. Under that kind of pressure, iron, the main ingredient in the core, behaves in bizarre ways. It might actually be part solid, part liquid, and could be responsible for generating Earth's magnetic field through its movement. So, if the pressure can be extreme in the core of the Earth, which is not the largest planet in the solar system, it got me wondering, what about larger planets like Jupiter? Well, Jupiter is so massive that as you go deeper inside, pressures skyrocket to the point where even hydrogen becomes metallic. Yes, metallic hydrogen behaving like a shiny metal that conducts electricity. This metallic hydrogen might be why Jupiter has such a powerful magnetic field, the strongest of any planet in the solar system. On Earth, scientists can recreate extreme pressures using something called a diamond anvil cell. You take 2 flawless diamonds, place a tiny sample between their tips, and squeeze. With this method, they can reach pressures of up to 300 gigapascals. That's about 3 million times atmospheric pressure. Diamond anvil cells set the record for the highest pressures we have achieved in labs. And like with Bose-Einstein condensates, diamond anvil cells are useful to us. They're not just a record. They let us study how materials behave deep inside planets, and sometimes discover entirely new phases of matter. And then there are neutron stars. These are the collapsed cores of massive stars, and the pressures inside them are so extreme that atoms themselves collapse. Electrons and protons merge to form neutrons, so you end up with a star made almost entirely of neutrons. Imagine cramming the mass of our sun into a sphere the size of a city, a sphere only about 20 kilometers wide. The pressure inside is so intense, creating matter that's so dense that a single teaspoon of a neutron star material would weigh about 4 billion tons. Now that is some extreme pressure for you. So we've talked about extremely high pressures, but what about the opposite? What happens when there's almost nothing there at all? Well, the lowest pressure you can get is a vacuum, and space is the ultimate testing ground for that. In the void between galaxies, the average pressure is about 10 to the negative 15 pascals. To give you some perspective, the air pressure around you right now is about 100,000 pascals. Space makes that look ridiculously crowded. Out there, you might have one atom drifting through a whole cubic meter of space. That's how empty it gets. But once again, scientists here on Earth have managed to create extremely low pressures. They managed something like 10 to the minus 13 atmospheres, which is pretty much emptier than empty space. So why does it matter? Well, low pressure environments are crucial for loads of cutting edge experiments, from particle accelerators, where you don't want your protons colliding with stray air molecules, to gravitational wave detectors, where even the tiniest disturbance could mess with a signal from 2 colliding black holes a billion light years away. Let's move on to extreme speeds. And of course, the ultimate speed limit is the speed of light. 299,792,458 meters per second, or 300 million meters per second. At this speed, you could travel about 7.5 times around the Earth in just 1 second. Now, physics tells us that you just can't go faster than that no matter how hard you try, at least not if you have mass. But the fun part is seeing how close we can get. Take particle accelerators like the Large Hadron Collider at CERN. Protons there are accelerated to 99.999999% the speed of light. At that point, weird relativistic effects kick in. Their mass effectively increases, time slows down for them compared to us, and they behave in ways that are just completely weird. But it's not all locked away in underground machines. If you listen to the very first episodes of this podcast about Star Wars, you may remember the part about hyperspace travel, where I talked about the Parker Solar Probe. This spacecraft, launched in 2018, is the fastest human-made object ever. As it slingshots around the sun, it's set to reach speeds of 700,000 kilometers per hour. To put that into perspective, that's fast enough to get from London to Sydney in under a minute. And yet, even at those unimaginable speeds, that's still basically crawling along compared to the speed of light. I think that's kind of humbling. The universe has set a speed limit, and no matter how hard we try, we're just playing catch up. At the opposite extreme, physics also hides some of the slowest processes in the world. Now, I think this is a particularly interesting one, because often extremes make us think the greatest, the fastest, the highest, the top end of the scale. But extremely low ends of the scale are also just as impressive and mind-blowing. My favourite example, the pitch drop experiment. It started in 1927 with a professor in Queensland putting pitch, a sticky tar-like material, into a glass funnel. Now, pitch seems solid if you poke it, but it's actually just an incredibly viscous liquid. Over time, drops form and eventually fall. Now, eventually is definitely the key word here. Each drop takes about 10 years to fall. In almost a century, only 9 drops have fallen. For decades, no one had even witnessed one live. Imagine waiting a lifetime for a single drop. Then finally, in 2014, the 8th drop was actually caught on camera, after 87 years of suspense. It's one of those experiments that definitely teaches patience, but also perspective. Physics isn't just about explosions and extremes. Sometimes the most powerful things are quiet and almost invisible, happening in the background. On the subject of the quiet, almost invisible, another hidden extreme is the power of magnetic and electric fields. On Earth, our strongest lab-made magnets reach about 45 Tesla. That's already enough to rip a credit card out of your pocket from across the room. But in space, enter the magnetar. Magnetars are a type of neutron star with magnetic fields up to 10 to the power of 11 Tesla. That's a number so big it's basically meaningless to our brains. To give some sense, if you were within about 1,000 kilometers of a magnetar, its field could literally distort the atoms in your body. It's a reminder that the physics of extremes isn't just numbers. These things do exist out there in the universe, waiting to be discovered. So, what do all these extremes tell us? Whether it's the hottest plasma, the coldest lab-made atoms, or the crushing pressures of the deep Earth, physics thrives on pushing the boundaries. But here's what I think the bigger picture is. Studying extremes isn't just about showing off weird facts. It tells us something really profound about the universe. It stretches our theories to a breaking point, because when we ask what happens if we go colder than cold or faster than fast, we often uncover the cracks in our understanding, and that is how new physics is born. I really like that because extremes force us to stay curious. They encourage us to go beyond what we can already see and ask what happens if we push physics and our current understanding of it to the edge. Are the rules the same? Do they still hold up? It's also an interesting reminder that even really familiar things like heat or speed can turn into really bizarre things if you push them far enough. The extremes show us the edges of what's possible, and often reveal something about what we feel is the normal world around us. Not that physics is normal at all. And as we've seen, by studying the extremes, we discover so much more physics. The fastest particles help us understand relativity. By cooling atoms to almost nothing, we unlock quantum mechanics. And by watching a drop of pitch fall once a decade, we learn more about the nature of solids and liquids. I think it's in those edges and limits of our knowledge where we can see the true rules of the universe most clearly. So next time you hear about some record-breaking science experiment, remember it's not just about bragging rights, although it is absolutely also about bragging rights. It's about stretching our imagination to meet the universe where it really is, strange, extreme, and really surprising. It's also really interesting thinking about this just after the last episode of this podcast, which was about sci-fi. We often think these crazy extremes of knowledge and science can only exist in fiction, but sometimes I think that you could argue the extremes that already exist in our universe are already so strange, perhaps even stranger than sci-fi. Yes, sci-fi is strange, but is reality stranger? Well, that's all for this episode. I hope you have enjoyed it. If you have enjoyed this podcast, please go and leave a review or a comment and recommend it. If you want more Schrödinger's chat related content, go and check out the Instagram account where you can find me at Schrödinger's Chat Podcast on Instagram. Here I post all sorts of content from extra bits relating to the episodes, science book recommendations, and just general nerdy science stuff. So if you enjoy the podcast, you'll definitely like some of that stuff. Do go and have a look. Thank you so much for listening. I'll see you in the next episode. Until then, stay curious and go and tell everyone about this extremely cool episode. Bye!